Today we're going to learn the method of Lagrange multipliers. To motivate this, let us look at an optimization problem first. So we're trying to find the extrema of this function, 2x plus 3y, subject to the constraint x squared plus y squared equals 4. And we're going to do it in two ways. The first way is what you already knew. By the way, and last time we did something like this where we had x squared plus y squared less than or equal to 4, and that was a domain. And if that were the case, then when we optimize, we have to look at both the interior and the boundary. The interior is easy. We learned this 2 videos ago. So we're going to focus on the boundary, like what I said last time. And focusing on the boundary, we have the equal sign, x squared plus y squared equals to 4. And now we can use the constraint to rewrite f. We did this last time for a different function. So let's do it for this function. So we have x squared plus y squared equals to 4. That means on this boundary, we have y squared is equal to 4 minus x squared. So y is equal to plus or minus 4 minus x squared, square rooted. The plus or minus is important, so I'm going to keep it there. So now let's work over here, and f of x comma y is equal to 2x plus 3y. And now I can substitute that in. So this is equal to 2x plus 3 times the square root of 4 minus x squared. Let me call this g1 of x. Or I might have g2 of x, which is 2x minus 3 times the square root of 4 minus x squared. So those are my two possible functions. So that's on the boundary. One is the top half, one is the bottom half. So now to optimize each one, this is single variable case now. Now we just take the derivative and set it equal to 0. Right? So taking the derivative g1 prime is equal to 2. We're going to use chain rule. The 2 will come out. The square root has a 1/2. Those cancel. There's a negative sign. So that's negative 3 over square root of 4 minus x squared. If you can't do this quickly, write it out yourself. But I'm pretty sure this is the case. And then g2 prime, I'll do these in parallel because they're very similar. 2 plus 3 over square root of 4 minus x squared. If we set these equal to 0, if we set this equal to 0, that means that 2 is equal to 3 over square root of 4 minus x squared. And then this one means that 2 is equal to negative 3 over square root of 4 minus x squared. Solving this, we just move the radical to the other side, multiply it over, and then square both sides. So we get 4 times 4 minus x squared equals to 9. And over there, we get the minus will actually get squared away. So it will be equal to negative 3 squared, which is also 9. So this is remarkable. We can stop treating both cases now. So if actually, now that I'm thinking about it, I think I did the derivative wrong. Yeah, there's an x here. Right? I was trying to show off my mental skills, but the derivative of negative x squared is negative 2x. So the 2 cancels out with this 1/2 from the radical, but there's an x left. Oops, sorry. Okay, so well, I'm just showing all my mistakes as I would usually do in class, right? All right. So here, then there's an x there, so then that's 9x squared. Okay, this looks better because I would prefer to solve this one than the other one that we had, because this one simply says that 16 is equal to, okay, I better do this right, correct, 13x squared. And so x is equal to plus or minus 4 over square root of 13. and now you find the y value, put it in, evaluate f at these points. I don't really want to do this anymore, so I'll just write dot dot dot. I'm sure you can figure this out. It'll be similar calculation to what we're doing in the next page. So let's just move on. So you can see that this method works. I hope that you can see that it's kind of tedious. I'm going to show you a better way. Here is sketching pictures. Sketch on the same graph the constraint curve. So let me try to draw a circle first. X, Y, draw a circle of radius 2. Alright, that's my constraint curve. And some level curves of the function f. So remember f, let me write it here. F is 2x plus 3y. Let's consider the constraint curve, sorry, not constraint curve, level curve 2x plus 3y equal to 0. So that means y is equal to negative 2 over 3x. Yeah, so it's something like this. And this is where f is equal to 0. On that line, f is equal to 0. How about here? At this point, x is 0, y is 2, so I get 6. If x is 6, then it will pass through here. 1, 2, 3. So this line is f equals to 6. They should probably be parallel. This is a linear function. I'm not drawing these very nicely. Let me draw another one. How about I draw this one? Where on the constraint curve is the function f biggest? This one is f equals 6, f equals 0. This is f equals roughly negative 6. So I think somewhere here, f is 0, 6. This is biggest. If we draw a bunch of constraint curve, if it's tangent to that constraint curve, then the level curve would be the biggest level curve. The f of x, y, this is a linear thing, so the level curves are just parallel lines. If you move the line as far as you can, the moment you're about to leave the constraint curve, that's where it's biggest. And this point, it's the smallest. So we're going to hold on to this concept and then make this thing algebraic. All right, so let's go to the back. We have Lagrange multipliers. This is the theorem. So we're assuming that f and g are both differentiable. And if f has a local extremement on the constraint curve, g, at a certain point, let's ignore this for now, then we have this equation. Right? This is called the Lagrange equation. It says the gradient of f is equal to the gradient of g times a constant. That just means the gradient of f and gradient of g are pointing in the same direction. So let me go back to the previous page for a moment and see what that means. So gradient of f, maybe it's pointing in that direction. Remember, gradient is pointing in the direction of maximum increase, and it's orthogonal to the level curve. We saw this maybe 3 worksheets ago. So that's what the gradient means. But for g, you can think of that as a level curve as well. X squared plus y squared equals to k. So our function is g is equal to x squared plus y squared, and this is a particular level curve. And for that level curve, we also have a gradient that's orthogonal to that level curve. And so if we have the level curve, the constraint curve, which we're thinking as a level curve of some function now, some multivariable function, if we have these two level curves are tangent, then their orthogonal vectors are pointing in the same direction. No? So that's the point. Right. So come back here. So that's this equation. So let's try to solve this. Try to work through this. So we want to pick a suitable function g. Here I set g of xy equal to 0. So from the previous page, in order for x squared plus y squared to equal to 4, x squared plus y squared minus 4 should equal to 0. It turns out that minus 4 doesn't really matter, so you could have left it off. Then you just have to change that 0 to a 4. And that part doesn't really matter anyway. So we pick this function, basically x squared plus y squared. Write out the Lagrange equations. The Lagrange equation is this one. Gradient of f equals gradient of g times the constant. So let's write out, since it's on the previous page, let me write it out first. F is 2x plus 3y. And so then the gradient of f is 2 comma 3. And g, just for symmetry, since even though I have it up there, let me write it here anyway. And then the gradient of g is 2x, 2y. So the Lagrange equation says gradient of f is equal to lambda gradient of g. So let me write that out. So that's 2 comma 3 equal to lambda, which is just a number that we don't know, equals to that times 2x, 2y. And you can rewrite this by coordinates, so we get 2 equals lambda times 2x, and 3 equals lambda times 2y. What was the point of all this? Is the theorem said that if we had a local extremum at P, then P satisfies this Lagrange equation. Think about how our critical points were used. We said if we had a local extremum, then then it's a critical point that satisfies that the derivative is equal to 0. Now our point satisfies some other equation. Instead of saying derivative equals to 0, we say that the gradients are equal up to a constant. So just like when we set to find the critical points, we set the derivative equal to 0 and solve. Here we're setting these two gradients equal and solving. And so the points that we found are not necessarily all going to be local max or local min, but they are the full spec candidate pool. Just like how our critical points, when we solve the equation, we might get too many of them, and some of them might be local max, some min, and some might be neither. We're going to do something like that too. So then we, oh, by the way, I said local earlier. Here, because we are on, for this case, we are on a constraint curve that is closed and compact, bounded. So we are going to have global extrema. But this works for local as well. So now, let's try to solve these equations. We've already rewritten them several times. This one to this one to this one. The last one I think is the most useful. So I could say that, you know, let's see, if x is let me write something first. Let me solve for lambda. Lambda equals 2 over 2x, and it's also equal to 3 over 2y. Well, technically this only works if x or y are non-zero, but if x were 0, if x is 0, then it says 0 times something is equal to 2. That's absurd. Yeah, that's not possible. So here, this only works because of this specific one. You need to be careful in general. No x and y are non-zero in this case, because if they had been 0, these equations couldn't be satisfied. So because of that, then we were able to solve this. And now I don't actually care about lambda. I care about the relationship between x and y. So from here I can see that y is equal to 3/2 x. So move y to the other side, x to the other side, y equals 3/2 x. And so now we have that, we could find the values. So that means then we know that g is equal to 0 Yeah, this is given to us. G is equal to 0, and when G is equal to 0 and Y is equal to 3/2 x, well, let me first write out. This is x squared plus y squared minus 4. But I know that y is 3/2 x, 2/3, 3/2, yeah, 3/2, whatever. So 9/4 x squared minus 4. So here we're using the fact that y is equal to 3/2 x. Alright, so now we can, rearrange and solve. So I think I see 13/4 x squared is equal to 4. So x squared is equal to 16/13. And so x is equal to plus or minus 4 over square root of 13. It's the same numbers as when we did it the first way, of course. But I think this way is different, and sometimes the math will be simpler, the arithmetic will be simpler, and sometimes it will be more complicated. And so you want to know both methods. And that's why we teach you both methods. Now, critical points. So we have 4 over square root of 13 and some y value, and negative 4 square root of over square root of 13 and some y value. Last one I stopped here because I was too lazy to calculate the y value, because it was complicated in the last one. There's x squared plus y squared equals 4. Here I have this equation, which makes it a little easier for me to calculate y. The y values are 6 instead of 4. Negative 6. Those are the critical points. Let me also say that there's this little place that says or gradient of g is equal to 0, and that's because of the caveat up here that says and if gradient of g is non-zero, then this whole thing works. So if the gradient of g were 0, then that might be a place to pay attention to as well. Right? So in general, you'll want to also check that condition. The gradient of g is, if it's not 0, then you get to do this. So if it is 0, then you cannot do this. That means you have to pay attention to that case where it is 0. Right? So I know this sounds a little backwards. If it's not 0, then we're done. But if it is 0, then we have to pay attention. Could it be 0? Well, x squared plus y. So the gradient, if gradient is 0, maybe we should do that one. So I'll do that right here. So if gradient of g is equal to 0, because gradient is 2x 2y there, so that means we get xy is 0 0. Yeah, that's the only place where the gradient is 0. And if that had been on the constraint curve, then we would need to pay attention, because this is not satisfied. The fact that it's not equal is not true, because it's equal. But over here, if you plug in 0 0, you get negative 4. It's not on the constraint curve. So in this case, we didn't have to care about that. I mean, we did care, but it didn't matter. So finally, calculate f at the critical points. These two, one of them will be max, one of them will be min. And from the picture from the previous page, we already know that this is going to be max, that's going to be min, but you should probably calculate it out. Right? So f of xy is equal to 2x plus 3y, and then now we can calculate f of 4 over square root of 13, 6 over square root of 13, that's equal to 8 plus 18, so 26 over square root of 13, and the negative 1 will be negative 26 over square root of 13. So then, because this is bigger and that is smaller, we know that this one is a max and that one is a min. And we're done. So that's it for today. The Lagrange multiplier method gives us a different way of doing constraint optimization. So you should know both ways, and I'll actually ask you to do homework, one problem in 2 ways. I force you to do both ways so you can see which way you prefer. Alright, that's it for today. Bye.